Hello. So now we're going to do this problem, which we're going to call a nut problem for obvious reasons. Well, for reasons that will become obvious once we've read it. Okay, and let's do that together. Let's begin by reading it together. So a nut mixture contains peanuts, almonds, and walnuts. By the way, let me also say this. The numbers here, I just decided to make them this way for the problem at hand. They bear no resemblance to the actual nutritional value of any of these nuts. Okay, it's just, these are just numbers I put together for the purpose of the problem. Okay. With that behind us, a little caveat there. So a nut mixture contains peanuts, almonds, and walnuts. Assume that each individual peanut has 3 grams of fat, 3 grams of protein, and 5 of goodness. Okay. Assume that almonds have 2 of fat, 7 of protein, and 6 of goodness. And assume, moreover, that walnuts have 5 of fat, 8 of protein, and 9 of goodness. Okay. Now, if the mixture as a whole has 120 grams of fat, 262 grams of protein, and 240 of goodness, how many pieces of each nut comprise the mixture? Okay. Now, admittedly, now I'm going to make a little comment here, which I'm sure some of you are already thinking. You're thinking, David, are you actually stating that there's a quantity of goodness associated with each nut? Are we to take you seriously about this? And so from a strictly honest perspective, I'm going to admit to you that I added in goodness as just another variable that we could use in this problem, and not necessarily as anything more than just a tool for me to create this problem for our discussion. Okay? That doesn't mean we can't take this problem seriously, because it will show us how to set up the problem in terms of a system of linear equations, as you might have already imagined. And we're going to be able to use that problem to solve. We're going to be able to use that as a model problem that we can solve for variables. Now, however, although admittedly what I'm saying, in other words, is that yes, goodness is not something that we can associate with a nut. Okay. Now, on the other hand, on a separate note, I will say that if you study economics, there is a concept called utility. And so the utility is basically a measure of how much benefit you get from some item. Now, that's not a technical definition of utility because I'm not an economist. But if you wanted to think about it in a serious way, you could say, well, maybe what David's talking about here in terms of goodness is a measure of the utility of each nut. And in this case, utility might be just, how much happiness you derive from it. If you have more utility, maybe you like that nut more. Maybe I like pecans more than I like peanuts, so maybe my utility for pecans might be a score like, let's say 10, while my score for 8 in terms of utility of peanuts might be a 7 or something, right? But anyway, that's just a separate note. But so for any of you who laughed about me using a quantity called goodness, yes, I'm using it solely for the purpose of creating this system of equations. But if you study economics, there may be a way for you to actually assign values like goodness to things like nuts, okay? Anyway, let's read that one more time, and then we're going to do the all-important process of setting up the system of linear equations, and then, of course, solving it to find out what this problem is asking, which is how many pieces of each kind of nut comprise the mixture, okay? So let's read it just one more time. So a nut mixture contains peanuts, almonds, and walnuts. So we have peanuts, almonds, and walnuts. Okay, we have 3 different kinds of nuts. 3 different kinds of nuts. We assume that each individual peanut has 3 grams of fat, 3 grams of protein, and 5 grams and 5 of goodness, whatever units you want to pick. Assume that almonds have 2 of fat, 7 of protein, and 6 of goodness. Walnuts have 5 of fat, 8 of protein, and 9 of goodness. And if the mixture as a whole has 120 grams of fat, 263 grams of protein, and 240 of goodness, and the question is how many pieces of each nut comprise the mixture? Okay, now with that stated, we can start to set up this problem, and let's do that together, okay? And the first thing we're going to do, as you might imagine, is we're going to label our variables. I'm going to let P, okay, denote the number of peanuts, A denote the number of almonds, and W denote the number of walnuts. Okay. Okay. So as we mentioned, P will be our number of peanuts, A will be our number of walnuts, A will be our number of almonds, and W will be our number of walnuts. Okay. Now, I always recommend, whenever you're solving a word problem, always choose an appropriate variable for the quantity of interest and notate what it's going to represent. Obviously, here I'm writing a complete sentence because I want this to be a model solution for you. But if you're like doing some word problem for some other situation, you can just put a very abbreviated notation. Oh, W num of walnuts or whatever, right? Okay, let's continue now. Let's look at what we can figure out. We know that we have 120 grams of fat, for example. We know that each peanut has 3 grams of fat, each almond has 2 grams of fat, and each walnut has 5 grams of fat. So if we want to think about the fat constraint, for example, we know that for each peanut, okay, I'm going to get 3 grams of fat. So I can say 3 times P, 3 times the number of peanuts, plus 2 times the number of almonds, plus 5 times the number of walnuts, will give us 120 and 120 grams in total. So you see, this is our first equation of our system. And this equation, as you already can tell from our discussion, represents the constraint on these numbers of peanuts, almonds, and walnuts that comes to us from the fact that the mixture has 120 grams of fat. So we can think of this as the fat equation. Okay. By the similar kinds of reasoning, we can look at what this constraint of protein implies about the relationship of these nuts, the quantities of these nuts. So, for example, I'm going to make the equation that captures that constraint for the protein. I know that I have 263 grams of protein in total. Now look at this. An individual peanut has 3 grams of protein. So I'm going to do 3 times P to represent the protein that comes from the number of peanuts I have, plus I know that each almond has 7 grams of protein, so it'll be plus 7 times the almonds, plus, and then with the walnuts, it's 8 of protein, so it's 8 times W. And then finally, we know that for the goodness, we know we have 240 total of goodness in whatever unit you want to imagine, okay? And you can see that a peanut has 5, so it will be 5P plus almonds have 6 of goodness, so 6A, and then finally walnuts have 9 of goodness, which means plus 9 times the walnuts. So we have finally set up this equation. The first equation represents our constraint from fat. Our second represents our constraint from protein. And our third constraint represents the constraint given to us by the amount of goodness, associated with each nut, and in particular with respect to this mixture. Okay. Okay. So this is our system of equation. And so now we're going to go into the process of actually solving the system. And I'm going to begin by solving it using substitution. And then after that, I'm going to do elimination. Okay? Yeah. Let's get started. So as I mentioned, what we're going to do is we're going to start with the substitution procedure to solve this problem. And then we're going to do the elimination method, okay? So because I want you guys to see me solve this system using both techniques so that we can, because I want you guys to be familiar with both techniques, okay? Now let me briefly begin with an overview of the substitution technique. Okay, so what we're going to do is we're going to take any one of these equations, okay, and we're going to solve it for one of the variables, either P, A, or W, it doesn't matter. And then, depending on which equation we pick, and depending on which variable, so for example, let's say we were to pick the first equation, and let's say I solve for P. Then I'm going to use that expression for P in terms of the other variables to substitute into the second and third equation to remove P from those equations, and that'll create a new system comprising, it'll be a new system that will consist basically of the two equations that I substituted the expression for P in, but because I had an expression of P in the remaining variables, this new system, which will be two equations, will no longer have P, and then I'm going to repeat that procedure to end up with one equation that only has one of the variables. Now I know that might have sounded a little bit confusing, but when you see me do the problem, I'm going to be highlighting to you as we go what happened in terms of that overview I just gave, and you're going to see that it's going to make sense what I'm saying. Okay? Okay. So now, in this particular problem, it's difficult to come up with a good idea of what to solve for. And so what I'm going to do is I'm just going to take the first equation and I'm going to solve it for P, and then I'm going to use that to plug into the remaining equations. Okay? So let's do that. Okay. Okay. So from the first equation, okay, I get 3P, okay, plus 2A plus 5W equals 120. I'm going to solve this for P. So what does that mean? That means that I'm going to get rid of, first of all, this 2A. I'm going to subtract it from the left, and I'm going to subtract it from the right. I'm going to get rid of this 5W. So I'm going to subtract it from the left. I'm going to subtract it from the right. That's going to give me, okay, this is gone, this is gone. I'm left with 3P equals to 120 minus 2A minus 5W. Okay? Okay. Now what I'm going to do now is I'm going to divide both sides by 3 because I want to get the P by itself. So here I'm going to divide by 3, here I'm going to divide by 3. Okay? That gives me P is equal to 120 divided by 3, okay, minus 2 divided by 3, A, minus 5 divided by 3, W, okay? Okay. And of course, you might already know this, but 120 divided by 3 is 40, right? So if I were to do this division over here, 3 goes into 120, 3 goes into 1, it doesn't. 3 goes into 12 4 times. Why? Because we have 3, 6, 9, 12, right? So that means it goes in 4 times. 4 times 3 is 12. 2 minus 2 is 0. 1 minus 1 is 0. Then I bring down this 0. I ask myself, how many times does 3 go into 0? 3 goes into 0, 0 times. So I put my 0 there. 0 times 3 is 0. 0 minus 0 is 0. There's no numbers left to drop, and so that's the termination point of the long division. So what I can do now is I can write, P is equal to 40 minus 2/3 A minus 5/3 W. And this comes from the first equation, okay? So now our strategy is going to be to plug this value for P into the equations 2 and 3. And what that's going to do is, if you notice, because this expression for P has A and W only, when I use it in the equations 2 and 3, I will come up with a system of 2 equations that are only in terms of A and W. And let's do that now. Okay. So this is what we got from the first equation. So now I'm going to plug this expression into the second equation, okay? So I'm going to get 3 times P. But what is P? P is this expression. 40 minus 2/3 A minus 5/3 W plus 7a plus 8w equals 263. Okay. See, I have replaced the expression for p in equation 2 with the expression for p that we got from equation 1. Okay. And so now what we're going to do is we're going to simplify it. First things first, I have to distribute this inside. 3 times 40, 3 times negative 2/3 a, 3 times negative 5/3 w, and then we're going to be able to combine all the like terms. So now 3 times 40, that's going to be 120. Okay. You could do that if you wanted on paper. You could say, okay, 3 times 40, 3 times 0 is 0, 3 times 4 is 12, and you can see it's 120. Okay. Now, what is 3 times negative 2/3? First of all, it's a positive times a negative, so I know whatever it is, it's going to be minus. And I claim to you that 3 times 2/3 is 2. Okay. Now let me show that to you here. 3 times 2/3. Okay. So first of all, I have a whole number times a fraction. How do I do that? I can convert this whole number to a fraction by setting it as the numerator and 1 as the denominator. So it'll be 3/1 times 2/3. Okay. Now how do I take the product of two fractions? The product of two fractions is the fraction whose numerator is the product of the numerators and whose denominator is the product of the denominators of the fractions being multiplied. In this case, 3 times 2 is 6 and 1 times 3 is 3. Then I ask myself, aha, I have the fraction 6/3. What is that? That's 2, because 6 divided by 3 is 2. Okay? Just as we saw there. Okay? By the same token, if you carry this process out for 5/3, you will get, so this is minus 2a, because it's 3 times 2/3 a, and then 3 times negative 5/3 w. I claim to you that that's going to be minus 5w, okay? Because 3 times 5/3, okay, will be 3/1 times 5/3, okay? Because, of course, I can rewrite 3 or any other whole number as a fraction by setting it as the numerator and 1 as the denominator, like I did here, okay? And then I take it the product of two fractions by, the product of two fractions is the fraction whose numerator is the product of the numerators of the fractions being multiplied and whose denominator is the product of the denominators of the two fractions being multiplied. So 3 times 5 is 15, okay? And 1 times 3 is 3. And then, of course, 15 divided by 3 is 5, okay? So that justifies that this is the distribution of this within this parentheses. So now I bring on the rest of this, okay? So plus 7a plus 8w equals 263. Okay? Okay. So now I need to combine like terms, and also I need to move this 120 to the other side. So I'm going to subtract the 120, okay? Subtract the 120. This is gone. Now look at this. I have negative 2a plus 7a. Aha. That will be a total of positive 5a. I have negative 5w. I have plus 8w. So that'll be plus 3w. Okay. And that will equal, now I have 263 minus 120. 3 minus 0 is 3. 6 minus 2 is 4. And 2 minus 1 is 1. So now look what has happened. My second equation from my original system, by substituting the expression for p that we got from the first equation, has now been transformed into the first equation of our new, let's say, subsystem. It's not really a subsystem, but it's gonna, well, I'll get to that in a moment. But this is gonna be the first equation that is gonna be part of our basically the system we get when we substitute for p using our expression from the first equation. Okay, so let me save that here. Okay, 5a plus 3w equals 143. But what's most important here, as you notice, is that I transformed an equation that had three variables, P, A, and W, into an equation that only now has two variables, the A and W, of course. Okay? So now we're going to do the same thing for equation number 3, and that's going to give us the second equation of this smaller system, to which we're then again going to apply the substitution method so that we can finally get the value for one of these variables, whether the walnuts or the almonds, and then from there we're going to then back substitute. Okay, so let's do that. So now what we're going to do is we're going to use this expression, we're going to substitute it into the third equation of our original system. Let's do that together here. So I'm going to take, let me see here. I'm going to take 5 times my P, but what's my P? It's this expression, 40 minus 2/3 A minus 5/3 W, okay, plus 6A plus 9W equals 240. Okay, okay. So now you can already see that just as before we had an equation from the original system that has P, A, and W as its variables, and in this formulation you can already see, even though we haven't simplified it yet, that because of my substitution, I now have only A and W in this equation. Okay, so now we're going to do the distribution. 5 times 40, that's going to be 200. Okay, we can do that multiplication. I'll show it to you right now in a moment. 5 times negative 2/3 A will be minus 10/3 A. I'll show you that right now as well. 5 times negative 5/3 W will be minus 25/3 W. Then we're going to bring this down. Plus 6A plus 9W equals 240. Now before I continue, I do wanna verify for you that what I claimed here about these coefficients being what they are is in fact true. First of all, 5 times 40, is that 200? Let me show you here that that is in fact 200. How do I get 5 times 40? Well, 5 times 0 is 0. 5 times 4 is 20. You can see indeed it is 200. How did I get 5 times 2/3? So first of all, the sign. Is it negative? I have a positive times a negative. The product of two numbers of opposite signs is always negative. Okay? So this is negative. Now the claim that I'm going to show is that 5 times 2/3 is 10/3. So 5 times 2/3. First of all, 5 is not a fraction. So I have to write it as a fraction. I'm going to set it over 1. And I'm going to then multiply it by 2/3. Okay? Any whole number, I can write it as a fraction by setting it as the numerator and setting 1 as the denominator. So now I'm going to carry out this product. How do I get the product of these two fractions? The product of these two fractions is the fraction whose numerator is the product of the numerators of the fractions being multiplied. 5 times 2 is 10. And whose denominator is the product of the denominators of the fractions being multiplied. In this case, 1 times 3. And there we go. That's the 10/3. In a similar way, I can get the 5 times 5/3, right? Right, so first of all, I want to do that. So first, I don't know how to multiply a whole number by a fraction, but what I can do is I can rewrite 5 as a fraction by setting it as the numerator and 1 as the denominator, okay? And I can multiply it with the 5/3, right? So now I have a fraction times a fraction. And so what can I do now? Well, the product of these two fractions is the fraction whose numerator is the product of the numerators of the fractions being multiplied. In this case, 5 times 5, which is 25. And whose denominator is the product of the denominators of the two fractions being multiplied. In this case, 1 times 3, which is 3. And so that, in fact, shows us that it is, in fact, the case that when you distribute the 5 into this parenthetical expression, that you do, in fact, get this expression. Okay? Oops. And so now what we're going to do is we're going to combine like terms and we're going to simplify this equation. Okay, so let's do that together. So first, I'm going to subtract this 200 to the other side. Okay? Okay. Okay. And so on this side, I'm going to have 0 minus 0, which is 0. 4 minus 0 is 4. 2 minus 2 is 0. Then what I need to do is I need to figure out what is negative 10/3 a plus 6a. Now, in order to do that, what I'm going to do is I'm going to calculate with the coefficients. What I'm going to ask is, what is negative 10/3 plus 6? See, because the combining of these two like terms will be basically negative 10/3 plus 6a. Okay? So that's what I'm going to do here. I'm going to combine the coefficients, and then that'll become the coefficient for the term with a. Okay? So let's do that together. So here I have a fraction, and I'm adding a number that's not a fraction. So as you know, I can't do this directly. I have to make the 6 into the fraction, and we're going to do it just as we were doing before. That is to say, I'm going to set it as the numerator and one as the denominator. So I have negative 10/3 plus 6/1. Okay? Now we have a problem. Now we're adding two fractions, but they don't have the same denominator. So I have to fix this. I'm going to multiply this fraction by a fraction which will allow me to force this product of the fraction of this fraction 6/1 with the fraction I'm about to place there. I'm going to force that product to have the same denominator as this fraction here. So let's do that together. So this is going to equal negative 10/3 plus 6/1 times some fraction. And I ask myself, what times 1 gives me 3? What times 1 gives me 3? Aha, that's 3. If I multiply the bottom by 3, I have to multiply the top by 3. And then what you can see here is that, just as I mentioned before, how do we get the product of two fractions? We multiply the numerators of the fractions being multiplied, and we multiply the denominators of the fractions being multiplied. So this ends up being negative 10/3 plus 6 times 3 is 18 over 1 times 3 is 3. Aha! Now that they're on the same denominator, to add them, I simply add the numerators. Negative 10 plus 18 gives me 8. So the result of this calculation is 8/3. Okay? So I have 8/3a. Okay? Because I've just combined this term with this term. Now, by the same reasoning, I'm going to need to combine the negative 25/3w plus 9w. Okay? So in order to do that, as you can imagine, I'm going to calculate what is negative 25/3 plus 9. Okay? And whatever the result I get there, I'm going to affix it to the w, because that will be because this will be the coefficient of the w when I combine the like terms. Okay? And as before, we can see that I can't add it directly. So what I first have to do is convert this into a fraction. Okay? Like this, right? And again, here I have two fractions with different denominators. And what I have to do is I have to multiply this fraction, the 9/1, by a fraction that will allow me to force the denominator of the product to be 3, so that we'll be able to combine it. Okay, let's do that together. Negative 25/3, okay, plus 9/1 times some fraction. And I can see, of course, that 3 times 1 would give me 3. So I'm going to force that to be 3 on the bottom and on the top, because now when I multiply this pair of fractions here, I will get a fraction that will have denominator 3, but which numerically has the value 9. I'm going to show that to you right now in a moment. Okay? So in other words, I have negative 25/3 plus 9 times 3 is 27 over 1 times 3, 3. Let me show something to you here. This process that we're going through, as you might be aware, is known as finding an equivalent fraction. And what that allows us to do is it allows us to write a fraction that has the same value as the original number, right? In this case, 9, because we really want to calculate what is negative 23 plus 9. But if you divide 27 by 3, you see that that actually equals 9. So all that this procedure does, it is allows us to rewrite the number 9 in such a way that we can actually perform the calculation with this fraction that has the denominator of 3. Okay? Okay. But anyway, so now that we're at this step, we have the same denominator, so all we have to do is add the numerators. In this case, negative 25 plus 27, that gives us positive 2/3, right? Because negative 25 plus 27 is 2 over 3. So now here, this becomes plus 2 over 3w, and that of course equals 40. And so this then becomes our second equation for our system over here. 8 over 3a plus 2 over 3w equals 40. Okay? Okay. And so look what we have now. So let me just recap where we are in the process. What we said originally was that the whole idea of substitution was that we take one of the equations from our original system, and in fact it doesn't matter which one we pick. Usually we just pick the one that'll give us the easiest approach to solving for a particular value. In this case, the easiest choice is not clear, so I just picked one of the equations. In this case, the first equation, solved it for p, okay? And what I used is I substituted in the second and third equation for p. I substituted for p this expression, and then I simplified those equations that I got from substituting for p with this expression, and I got this system. So in other words, this system comes from the second and third equations of the original system, okay? And of course, had we picked, let's say, the second equation, we would have plugged the expression. Let's say we had solved for p in the second equation in their first step. Then we would have substituted that expression for p in equations 1 and 3, and this system would be basically the result of those calculations. So this would be drawn from equation 1, and this would be equation 3 in that alternate scenario. In this scenario, these equations are basically the results of having performed the substitution in equations 2 and 3, and we're now going to perform this. We're going to perform the substitution method on this smaller system of equations, and this will enable us to actually get to a numerical value, okay, for one of the variables. Now, here, it's not entirely clear which equation is simpler to solve and for what variable, but it doesn't matter because ultimately we have to solve for one of the variables. So what I'm going to do is I'm going to take this first equation from our new system, and I'm going to solve it for, let's say I'm going to solve it for w, okay? So let's do that together here. 5a plus 3w equals 143, okay? I now, I'm going to solve it for w. So I'm going to subtract the 5a to the other side, and I'm going to subtract the 5a to the other side, okay? I get, therefore, 3w equals to 143 minus 5a, right? Then I divide by 3. So I divide by 3, divide by 3. And I end up with w equals 143 divided by 3 minus 5/3 a. Okay. Okay. So this expression came from the first equation of this new system. Okay, let me delete this over here so that we don't cloud this. Okay, okay, okay. So now what we're going to do is we're going to take this expression for W and I'm going to substitute it into this second equation from our new system. Okay? Because again, you have to take the expression for whatever variable you solve and use it in the remaining equations. In this case, there's only one remaining equation, so we're going to plug it in here. So let's do that together. So let's look at this equation here. 8 over 3a plus 2 over 3w. Well, what is w? It's this. It's 143 over 3 minus 5/3 a, right? 2/3 w equals 40. Okay. And now what we can do is we can, well, first of all, we can observe that now there's only a in this equation. There's no other variables in here. So we're actually going to get a numerical value for a, which we'll be able to use to back substitute into the rest of the equations to get a value for w and for p. Okay, that's number one. Number two, there's lots of things that we could do to make this calculation a lot easier. And so, for example, what I could have done is, before I plugged in, I could have multiplied this equation by 3 on both sides to get rid of this denominator. Okay, but let's not worry about that right now. Let's proceed with this, but I just want to let you know that those kind of possibilities are available for you when you're doing the calculation. You don't have to do it exactly the way I do it. The main idea that I want you to get from this is the idea of substitution and how we do it. Okay, so now let's look at this together. What we have to do is we have to apply the distributive law to this fractions, to this expression here. So for example, here, so let me bring this down first. 8 over 3a plus, here I'm going to multiply these two fractions first. 2/3 times 143 over 3. I know that when I multiply fractions, the product will be the product of the numerators. So 2 times 143 will be 286. And the product of these two fractions will have the denominator. That is the product of the denominator. So it'll be 3 times 3, which will be 9. Okay. And then I'm going to multiply these two, right? Because I multiply this with this first, and then I multiply this with this second. Okay. So here I have a positive number times a negative. So it'll be minus. And then I have these two expressions. I know that I'm going to multiply the coefficients, basically. So what's 2 times 5? That's 10. 3 times 3 is 9. And then I bring my a, and then that equals to 40. Okay? Okay. And so, okay. So actually, what I can do now is let me see here. So I have several different possibilities. One of the things I could do is I could multiply the whole thing by 9, and that will make our lives a lot easier. And so, let me see here. Should I do that? Let me actually not do that yet. Let me do one little thing, and then we'll do that together. Okay. So the first thing I want to do is I want to combine these like terms of these like terms that have a in them. So in order to do that, I'm going to find the coefficient. So what is 8/3 minus 10 over 9? Notice I'm performing the calculation of the coefficients of a, because that calculation will give us the coefficient of the a in the reduced equation. Or in other words, this is what you would do on the scratch paper on the side. So I want to subtract these fractions, but there's a stumbling block here. This denominator does not match this denominator. Now, if I look at these two fractions, I can see, I can see that I can multiply 3 by some number to get 9. So I don't have to worry about multiplying both of these fractions by a fraction to get the same denominator, which would be the case, for example, if the denominators had been 2 and 7, and I couldn't multiply one by a number to get the other, by an integer to get the other, right? Here we have this nice situation where if I just multiply this one equation by 3 on the bottom, I'll get 9. And so I know that that'll be a nice little efficiency that we can do to accelerate this subtraction. Okay. So now look at this here. This space represents the fraction. I'm going to multiply this fraction by to get the equivalent fraction that I'll actually be able to use to perform this subtraction. As we mentioned before, if I multiply the bottom and the top here by 3, I will get what I want. That is to say a denominator of 9, and that will enable us to perform the subtraction. 8 times 3 is 24. 3 times 3 is 9. Minus 10 over, minus 10 over 9. Now, they're in the same denominator. I can just subtract the numerators. 24 minus 10 is 14. So this becomes 14 over 9. Okay. So I get 14 over 9a plus 286 over 9 equals 40. Okay. So now you can see that we're in a better position now. So now what I'm going to do is I'm going to multiply both sides by 9. And what do I mean by that explicitly? What I mean is that I'm going to multiply the whole side by 9. Okay, this is a common error that a lot of my students make, and I don't want you to make this mistake, okay? So when I multiply the left-hand side by 9, I put it in parentheses because I want to make sure that I don't forget I'm multiplying the whole thing by 9. And then, of course, the right-hand side is just a single number, so when I multiply it by 9, I'm just multiplying that one term, but that's only because it's one single number. If it was some expression, I would also have put it in parentheses because the 9 that I'm multiplying on the left-hand side would also have to be multiplied on the right-hand side to everything also, okay? Now, 9 times 40, that's 360, okay? And the nice thing that happens here is that this 9, basically, when I multiply it by this expression, we get rid of the 9 on the bottom. So this will be 14a plus 286 equals 360. Okay? And because when I do the 9 times the 286 over 9, we end up getting rid of this 9 with that 9. Okay? I'll do those calculations right now so you guys can see that. Okay? But we get this. So in other words, I'm going to ask you guys to accept this line here. Then I get rid of the 286 by subtracting it to the other side. Subtract the 286 here. Okay. So now how do we do the subtraction? Well, we're going to have to borrow. So let's do that together. 0 minus 6, I can't do it because 6 is bigger than 0. So I borrow from this 6. This becomes a 5 and this becomes a 10. 10 minus 6 is 4. 5 minus 8, can't do it. Why? Because 5 is less than 8. So I have to borrow from here. This becomes a 2, this becomes a 15. 15 minus 8, that's 7. Okay? And then 2 minus 2 is 0. So I get that 14a is equal to 74. Okay? Now, what I need to do is I need to divide both sides by 14 to get the a by itself. Okay? And so here, if you perform this division, you will see that it's 5 and 4 over 14.